Are you going to turn down one or are you just going to check it?
I think I want you to turn it in. Yeah. Yeah, because it'll take me too long to go around checking it. Does anyone need their exam from last time? I also remember to bring the sign-in sheet if you want to come by and visit me in my office if you have not done so. Anybody interested? You need that also? Okay.
But we have to reschedule.
There you go. Uh-huh.
Thank you.
Mm-hmm.
I want you to know that all that work, when you posted this, and you just heard a scream in the back, and my manager was like, "Are you okay?" And I was like,
Sure.
Happy scream?
Yes.
Oh, good. Yes.
Would you mind if I just rewrite it? Because I have a composition, and when I'm in the process of tearing it, like...
Yeah. Yeah. When are you going to rewrite it? Right now?
I was going to do it right now.
Okay. All right. That's fine. Okay. Let's get started. I don't know why I'm chit-chatting up here. So yeah, how was that problem?
I think it was bad.
Yeah, I mean, not too bad. That was what? It was to the 6th power? What was it? 4th power? Yeah, so it's not so bad. Okay. So why don't we turn that in, and I will count that as a quiz. I think I did ask you to put it on a separate piece of paper, right? How's work going, man? Yeah.
"Just rewrite it. I'm sure you'll know."
Yeah, I'll take it. Let's see how many people actually did it. Yes, please. If you didn't do it, you can turn it in next week, but the highest you can get would be an 80, okay? Yes. You-
Can I tune in how he said right now afterwards? Since I have to rewrite it?
Yes, you showed me it, so that's okay. But you know what? I mean, focus on this more than rewriting that. I'd rather you turn it into me later on than to. Okay. All right. Anyone else? Yeah. What? Okay. Here we go. So, trigonometric substitution. So the first part of this note says after we have mastered the above concept. So after we've done all the 30-something homework problems from 6.2 that you were supposed to have done today, after you've got that all figured out, then we can start to do these problems, all right? So what we're going to be doing is an interesting type of substitution. It's a substitution we have not ever done before, all right? And it's going to allow us to do some rather complicated functions, integrate some rather complicated functions. So the substitution that we're going to be using is called Trigonometric Substitutions, or I'm going to call it Trig Sub. All right, so here's the general idea, and this is really kind of confusing to read. I think I'll actually go through the time to kind of work it out by hand. So let's say we have an integral. All right, and somewhere in the integral, we have something like that. Somewhere, now that can be anywhere in the integral. All right, it can be in the numerator, denominator, it can be mixed up with other stuff, but you clearly have a square root. You've got something squared. Now this right here is a constant. All right, so this is some constant squared minus then your variable squared. Let's say we have that in there. All right, then one thing we could do is this. We could come in here and we could say we are going to replace x with a sine of theta. Now that is a weird substitution I'm making because I'm taking the letter x in the problem, right? And I'm replacing it just on my own free will, okay? I'm just coming in here and saying, all right, I'm going to replace x with something more complicated than x, right? So that means everywhere I see x, I'm just going to switch it out for an a sine theta. And that seems like, whoa, why are you doing that? It's going to create headaches, right? But let's just see what happens, all right? So let's notice a couple of things here. First of all, if I'm going to let x be a sine theta, then do you agree that x squared is a squared sine squared theta? Right, you just square each one? Okay, so check, that's true. Now, what would a squared minus x squared then be? Okay, so if x is this, then x squared is that, right? Then what's a squared minus x squared, which notice is that, right? Yeah. Okay, so what is that equal to? Well, it's a squared minus x squared, but x squared was that. A squared sine squared theta, right? And notice that both of these terms have a squared in them, right? So I can factor an a squared out, and I'm left with 1 minus sine squared theta. And what is 1 minus sine squared theta? Cosine squared theta. Pythagorean identity, right? Sine squared theta plus cosine squared theta equals 1. So this becomes a squared cosine squared theta. Okay. Well, why is that valuable? Well, let's keep going. Let's retrace our steps. If I say x is this, then x squared is that, and a squared minus x squared is that, right? Then the original square root that we had over here, let's see what it turns into. It's the square root of a squared minus x squared, which is the square root of, well, what was a squared minus x squared? This, right? So this is a squared cosine squared theta. And since they're both squared, and I'm taking the square root, and that's multiplication, you just square root each one, you get a cosine theta. So what this does, all right, is if we see a square root that looks like this, and we replace x with this, which is very strange, then we're going to be able to rewrite that nasty root as some cosine function. And I feel pretty comfortable integrating cosine functions, right? As opposed to something like this, which is typically harder to integrate, all right?
So would you always let x be a times sine to theta?
If it looked exactly like this, a squared minus x squared.
Only in that case.
Only in that case. Now, if it turns out it's a squared plus x squared, we're going to have a different substitution. Okay? Now, notice the substitution I made. I replaced x with a trigonometric function, right? This is why we call it trigonometric substitution. We are making a substitution of x for a trigonometric function. So depending on if this is a squared minus x squared or a squared plus x squared, or you could even have the x squared in front, x squared minus a squared, there are going to be 3 different substitutions that we can make. This is the first one, all right? But it has to look exactly like that to do the substitution. Okay, now let's talk a little bit more. I know that if I make this substitution, that this root part is going to become this, right? But remember in an integral, you always have that dx. Remember dx is always there? If we're going to rewrite the integral, replacing x's with stuff with thetas in them, then the dx is going to have to switch over to something with thetas in it also, right? So what would dx have to be replaced with? Not quite, because this is x, right? So in order to figure out what dx would be, I have to take the derivative of this. So what is the derivative of this with respect to theta? So take the derivative of the right side. A is a constant, right? Yeah. What's the derivative of the sine theta? Cosine theta, right? So the a comes for the right because it's a constant. Derivative of sine theta is cosine theta. And therefore, if I just multiply both sides by d theta, I have something I can replace dx with. So these 3 boxes are like the main components to this particular trigonometric substitution. If we make this trigonometric substitution, then the root thing will turn into a cosine theta. The dx will turn into a cosine theta also, d theta. And anywhere else that I might see an x, I'm going to replace it with a sine theta. All right?
So if it had a dx at the end of that, it would be a cosine theta times a cosine theta d theta?
If what had a...
If it had a dx at the end.
Yeah, let's do one, right? Because this is not an integral, right? This is just an expression. So let's do an actual integral now and see how we piece it all together, okay? So let's start out with integral. Let's go. I'm going to do one that we could do. This is one that we could do. Let's replace that 1 with 4. Let's make it a little more interesting. We actually could do this with substitution, all right? There is a pretty clever substitution where you let u be 4 minus x squared, you peel off an x, and it will work. And it's actually easier than what I'm about to do. But for this first example, let's just work with this problem and see how this would work, right? Because there are problems that I can give you where a cute little substitution will not work. In trigonometric substitutions, your only option, okay? So let's see how we're going to do this. So I look at the integral, and I realize that I do have a square root of a squared minus x squared, yeah? Okay, so let's first identify what's a in the problem. So I know that I'm going to be using trig sub, right? So I won't write this down every time, but I'm going to put, I have square root of 4 minus x squared. I'm doing some scratch work over here. This means that a is 2, right? Because 4 is 2 squared. Because I have the form of a squared minus x squared, I'm going to make the trigonometric substitution. Trig sub is what I'm using here. And I'm going to let x be what? A sine theta, right? And what's a? 2. So I'm going to replace x with 2 sine theta, right? Now I'm not going to go through the whole thing again and I'm not going to square x and do all that stuff. I'm just going to go to the main result, which is that this should turn out to be what? So go back and look at those 3 boxes we had. If x was a sine theta, then the square root of a squared minus x squared turned into what? A cosine theta, right? So this should turn into 2 cosine theta. You realize you would get that, right? You would just square this, put that here, factor out a 4. Yes? Okay. So that turns into that. And then also, dx will automatically turn into what? You can even see it right here. Just take derivative on both sides. 2 cosine theta. Okay, so I'm going to box these. I mean, these are my 3 main components, right? And now what I do is I rewrite the integral. Okay, let's rewrite the integral. So when I rewrite this integral, what is x cubed replaced with? Well, this is x, right? So if you cube x, you're going to cube both sides of that. So you cube the 2 and you cube the sine. So that x cubed out there is going to become 8 sine cubed theta. Hey, sine to an odd power. Hey, last class, right? Okay, what does the root turn into, that root thing? 2 cosine theta, so times 2 cosine theta. And then very important, what does the dx get replaced with? 2 cosine theta d theta. See that? I've rewritten the problem with trigonometric functions instead of x. Now let's clean that up. We've got a bunch of constants, right? 8 times 2 times 2, what's that? 32? I can pull out 32. I've got sine cubed theta and cosine squared. Okay, now based upon last class, to do this, what do? We're going to peel one sign out, right? Because we have an odd power of sign. So we're going to peel one sign off. So we have 32 integral. We've got sine squared theta because we peeled one off. We have cosine squared theta. We didn't touch that one. Here's the sign that we peeled off, d theta. And we know that this right here is going to be the du, so to speak, because we're about to make a basic substitution. So the basic substitution we make here is what? U is cosine theta. Cosine theta. Cosine theta. And then du is negative sine theta? D theta? And it almost matches, right? This is this is that. We're off by a negative.
Yeah.
So we just multiply both sides by -1. And now it matches perfectly. So I'm going to go in, anywhere I see a cosine theta, I'm going to replace it with u. Anywhere I see sine theta, d theta, I replace it with negative du. That's there. So I've got this taken care of and this taken care of. This I don't. So how do we deal with that? Pythagorean identity. So this is 32 integral sine squared is 1 minus cosine squared. And then cosine squared theta, and then sine theta d theta. And now I think I'm ready to replace everything. So 32 integral 1 minus u squared times u squared times negative du, right? Negative du? So I'm going to put that negative out here on the 32. Any questions on where I got any of that? Sure? Now we get to do what? Just distribute, boom, boom. Negative 32, integral, let's see, u squared minus u to the 4th du. Yeah, this is just because I'm kind of anal about this. I don't know why. You don't have to do this step. I don't know. I just don't like the negative out there, so I bring it back in and it changes the signs here and I reorder them. That's just like a personal thing, and you don't have to do that step. Okay, now, antiderivative of each one of these, right? Yes? Okay. The antiderivative of, we've got 32, let's see, 1/5 u to the 5th minus 1/3 u to the 3rd, then all of that plus c. You doing okay? Sinuses bothering you? Allergies or something? You're sick. It's allergy. Okay. Everyone around you kind of. Okay, so we're not done. Let's distribute the negative or the 32 through. What was u? Cosine theta. So this is cosine to the 5th theta, right? Minus 32 over 3 cosine to the 3rd theta plus c. Y'all agree with that?
Yeah.
We're still not done. Because the original problem had what variable in it? X. And right now our answer has theta in it. So we've got to get everything back to x now, right? Okay, so how do we get back to x? Well, what we do is we go back to where we had a relationship between x and theta. And that was the first thing we did, which was x was 2 sine theta? Yes? Yeah. 2 sine theta, right? That's what we had. We also had some other relationships. Didn't we say that the square root of 4 minus x squared was 2 cosine theta? Yeah. We did, right? Now I'm going to write that down over here, but I'm not going to use it. Didn't we say that this was that? We said that way a long time ago. So couldn't I just divide both sides by 2 and I would have cosine theta? And then I could just replace this cosine theta with that expression? I could, right? That's because we had it, right? But this is not always going to happen. You're not always going to have like cosine theta sitting there. Like, you're not always going to have what you're looking for over there sitting here. So I'm going to show you how you can get this from the original trigonometric substitution. And the way you do it is you first isolate sine theta. So you put x over 2 is sine theta. And then you do something that we did a long time ago. I think one of the first days of class, we drew a reference triangle. So I'm going to draw a reference triangle, which is a right triangle. And this triangle is going to be a picture of this equation. So I'm going to put my angle theta here. And then I'm going to remember that sine means opposite over hypotenuse, right? So opposite side would be x, and this would be 2, right? Pardon? Yes? All right. So this picture is the picture of sine theta is x over 2. Now, I'm interested in knowing what cosine theta is. So cosine theta off this picture is the adjacent side over 2, right? Now, you'd have to solve for this adjacent side, which you could do, and you would find that this is 4 minus x squared, because it's that squared minus that squared, but then the square root. Okay, so that would be the adjacent side. And notice that adjacent over hypotenuse is exactly what we would have gotten a second ago with that other equation. But this is more constructive because it may have turned out that our answer over here was like tangent theta. Okay, and if it's tangent theta, you don't have any information on it. You have to go with this, create the triangle, then tangent would be here. So it just depends. All right, so we're ready for the final answer. Here we go. We have 32 over 5. And then cosine theta to the 5th minus 32 over 3, and then cosine theta to the 3rd plus c. But cosine theta is that over that. So root 4 minus x squared all over 2, and then root 4 minus x squared, and then all over 2. We could do a little bit more, just in terms of cleaning it up. I mean, we could. Like, we could rewrite this like fifth power on, we could take the fifth power on this and the fifth power on this separately. And 2 to the 5th would be what? Two times 2? Times 2? Times 2? Times 2? 32, right? So if I did this fifth power on this 2, it would actually cancel that 32 out, wouldn't it? So I could rewrite this as 32 cancels out 1/5, and then I still have this root to the 5th power, which is the same as writing it to the 5/2 power. Right? That's the same as the square root to the 5th power. Y'all understand my 2's gone, my 2 to the 5th is 32 gone, right? Now over here we have 2 cubed, right, which is 8. And 8 goes into 32 how many times? Does it? 32? 8? Yeah, okay, 4? Okay. So that would become minus 4/3, because the 32 over 8 would go away. And then this would be 4 minus x squared to what power? 3/2. Plus c. So I claim that if you take the derivative of that, you will get back x cubed times the square root of 4 minus x squared. What do y'all think?
Were you painting today?
Hmm?
Were you painting?
I got into a little bit of an argument with my
All over.
Yeah, I know. It's the spray gun kind of got out of control today. I was trying to paint something before the weather changes because it's, you know, yeah. So, is it tonight? Yeah, I was trying. I'm hoping it'll dry. It's probably still too humid to have done it, but oh well.
I think you might have picked the wrong time to do it.
Yeah. Well, I didn't paint like it's something I painted in my garage.
Oh,
So it's not gonna get wet, but it's gonna take forever to dry. Yeah, and the paint gun, you know what? I won. It got me, but I won. I won that battle. What's that? I painted some furniture I built. Yeah, I'm so disappointed because I needed to have practiced a little more with the paint gun before I did it, but
Is it one of the air ones?
yeah, it's an air one. I've used it before, but you know, each paint is different, right? So, oh well. I had a couple of running spots, you know. It's not perfect, but
You might be able to buff it out.
I think I might be able to. Wet sand or something. I don't know. We'll see, but I'd say 90% of it is good. So, all right, that was fun, right? That was fun. Let's take a look at, so this is a summary of what you do when you see square root of a squared minus x squared. What you do is you replace x with a sine theta. Then that means automatically the square root of a squared minus x squared will turn into a cosine theta every time. And dx will always be a cosine theta d theta every time. All right? That's basically the problem we just did. All right, a little different, but that's basically it. All right, well, what if we have a different expression? So that was a squared minus x squared. Here's what we would do. What if instead we had a squared plus x squared? That little tiny difference of an addition sign underneath the root. Well, we use a different trigonometric substitution. And the one we use is a tangent theta. Now, let's see why that would work. If we let x equal a tan theta, then let's see if we can't figure out what a squared minus x squared would be. What would a squared minus x squared be? So a squared minus that squared, right? So a squared, not plus, sorry. I want plus. Trying to figure out what this is. So this would be that, and then tangent squared theta. And then what could I factor out of both of those? A squared, and what would I be left with in parentheses here? 1 plus tangent squared. And isn't that a Pythagorean identity? That is secant squared, isn't it? Therefore, if I take the square root here, it would be the same as taking square root here, which would just leave you with a secant theta. And that's why it says, if we see a plus here between these, we're going to go a tan theta, then that root part is going to become a secant theta every time. And then the derivative, dx, would be a secant squared theta d theta, and that's just because if you take derivative of that, you get a secant squared theta d theta, right? So the plus made a difference because the Pythagorean identity that we were going to need is different, right? The previous one, it was a minus something, so it was nice to have sine squared here, so we turned it into cosine squared. Here it's plus, so we need an identity that would work for us, so that one works. And then finally, the third and last form that we could see would be if we had the x squared minus a squared. Okay? On that one, we use a different one. And let me just remind you, we have to be a little careful here. If you see this versus this, these are not the same thing, right? These are not the same thing. And you cannot do anything to this to turn it into this. Some people try and say, oh, well, I'll factor a negative out. And then the negative, that makes that a negative a squared, and then it makes it a plus x squared, like that. Would you agree with that? Like distribute negative here, negative there, you get back this, right? I agree with that. But that negative right here can't like come out of the root, or, you know, right? That's the square root of a negative. That's like imaginary numbers and stuff. Like, you can't just bring that out. So there's no way to easily turn that into this. So that means we have a separate method for this, because our Pythagorean identity is going to look different. So the method we use is that we'll replace x with a secant theta. And then when you do all this, x squared minus a squared, when you do that, I'm not going to work it out. It'll spit out an a tangent theta. And then if you take the derivative of this, unfortunately you get a secant theta tangent theta d theta. But that's why we did the last class, because we could deal with secants and tangents inside of an integral. Okay? You all right? All right? Okay. All right, let's just try and do some examples now. All right, we're going to do this one, 1 over x squared root x squared plus 9. dx. I think it's worth it for us to make sure we can't do this with another method. Because I think you can appreciate just from that first example that if we do trigonometric substitution right now, we're going to be here for a little while, right? Okay, so let's just make sure we can't get it with anything else. A basic substitution. Do I see something in its derivative? Not really, right? I mean, we did play some funny games, especially on the last exam where you could like rewrite this as like x times x and peel an x off, right? But see, this x squared is down in the denominator. So you can't peel an x off. That x wouldn't be up top. It would be down on the bottom, right? Man, I don't see it. Do you? Do you see any substitution we can make, an easy path? The previous problem, there was an easier way to do that problem. All right, this one, there's not. Do y'all believe me? Do you see that there's not an easier way? So, and maybe this is the first problem that you look at and you understand why I don't give the first test covering all the techniques. Because if I gave you this and now you could use trigonometric substitution or integration by parts or U sub, and you don't know which one it is, you're going to take a little more time trying to figure out what to do, right? All right, so this is trig sub. What's the trig sub? So we need to identify that as either root a minus x squared, root a squared plus x squared, or root x squared minus a squared. It's obvious, right? It's the plus one. So for us, we're looking at root x squared plus 9, which means the a that we're working with here is what? 3. Okay. Now, what is the trigonometric substitution that we're going to make? X is equal to 3 tan theta. So where'd you get that from? Did you write it down, or it's in the notes? I believe that it's also on a formula sheet that you're allowed to have on a test. Who has the formula sheets printed? Do you see it? I believe there's a formula sheet. It's not the packet, the reference sheets. There are some additional sheets on the website. I want to make sure they're on the website. They should be. It's not in the reference pages, no? It says like, that's it, right? Yep, okay, can I see that? It says trigonometric, trig integrals and substitutions. The first part of this talks about previous class. And then the very bottom is the 3 scenarios and what substitution you make. All right, so you don't even have to remember that. When I was in Cal 2, I had to remember that. But I'm not asking you to remember that. Just you need to know how to use it, all right? So here we go. We're going to go x is 3 tan theta. Automatically, this tells us that x squared plus 9 is going to turn into what? So I would make sure you have that formula sheet, if not the notes. Here's what it says. If x is equal to a tan theta, then the square root part's going to turn into a secant theta. So for us, it's going to turn into what? 3 secant theta. And finally, we know that dx will turn into, well, all you have to do is take derivative of that. But it's also on the formula sheet. 3 secant squared theta d theta. Right? Okay. Any questions on those 3 things? Rewrite the integral. 1 over. Okay, x squared. Well, that's x, right? So x squared is that squared. So 9 tan squared theta. And I better extend this out. What about the root there on the bottom, the root x squared plus 9? 3 secant theta, that goes on the bottom. And I'm a little bit concerned right now because this is starting to look pretty nasty. However, I still have a dx here. What's that dx? 3 secant squared theta, and that's, you could argue like that's up top, right? That's on the top, that secant's on the bottom. And I think we're done, right? Okay, so if that's it, let's clean it up. I think we get some things to cancel. We've got 3's gone, and then one of the secants is gone, right? So my new integral is 1/9, and then I've got secant theta over tan squared theta d theta. Do you agree? Yeah? How do we deal with that? So that's not exactly like the problems we did last class, because the problems we did last class, when we had tangent and secant, they were together in the numerator, weren't they? And here the tangents and secants are separated. So let's just check real quick. Do we have a basic substitution? Like if I let u be tangent, the derivative is secant squared, which I don't have, right? So there's not a basic substitution. I would never want to say let u be secant because the derivative of that is secant tangent and everything I have left is down here. So I wouldn't want to do that. So we kind of get a little bit jammed up at this point. So what I would recommend you do is anytime you have an integral that has secants and tangents and things like that, and it's not quite like working out, just rewrite everything in terms of cosine and sine. Do you agree with that? That's secant theta over tangent squared theta, right? And now a fraction over a fraction, you flip, right? So we just do reciprocal like this, and it comes up. So we have 1/9 integral 1 over cosine theta times cosine squared theta over sine squared theta, d theta. And one of the cosines cancels. And that gives us 1/9 integral cosine theta over sine squared theta d theta. So there's no guarantees, but maybe that's easier to work with. What do you got? What can you do with that? Let cosine theta be u, then the derivative would be downstairs. But you're close. We could use a half angle on this to get the, you mean to power reduce that? The problem with that is that you would then have a 2 theta in there because you remember the trade-off is that you power down but you double the angle. I think y'all are trying too hard. U is sine theta. U is sine theta. The derivative of that is what? Cosine theta d theta. It's right there, right? So if you let u be the denominator, the sign down here, the derivative of that is right up there. So this is just a basic u substitution now. So now I make that substitution. U is equal to sine theta. Then du is cosine theta d theta. And I'll be able to rewrite the integral because everything like matches perfectly, right? So 1/9 integral what? 1 over u squared? U to the negative 2? 1 over u squared? And then du, because d theta is cosine theta d theta. I have it exactly. Cosine theta d theta, that's just du. And now I use the power rule. Right? Okay. So the power rule tells me that this is equal to Careful with the power rule here. We're taking an antiderivative, right? Not a derivative. So what do we can get? Negative 1/9, right? That negative comes out, all right? And then u to the what? Negative 1 plus a constant. Just adding 1 to the power, right? And let me just rewrite this. This is negative 1/9 times 1 over u. How about that? Plus c. I'm only doing that because I already kind of know what's about to happen. What was u? U was sine, wasn't it? Now be careful. If you put sine right here to the negative 1, that does not mean arc sine. That doesn't mean the inverse function. It means sine raised to the negative 1, which is 1 over sine, right? Those are two different things. So this becomes negative 1/9 times 1 over sine theta plus c. And what is 1 over sine by definition? Cosecant? So this is negative 1/9 cosecant theta plus c. We're done? No, we're not done. The problem had x in it. Our answer has thetas in it. So we got to get it back. We've got to get back to x now. Right? All right, so let's get it back to x. To get it back to x, where do I go? Go all the way back to your trigonometric substitution. Okay? Our trigonometric substitution, the one that we made, was x was equal to, I forgot, 3 tan theta? I said this is what we're going to use to draw a reference triangle. So I divide both sides by 3 so that I can isolate tangent. I draw a right triangle. Theta's here. Tangent is opposite over adjacent. So this is telling me opposite over adjacent. And then I can always solve for the hypotenuse if I know two sides of a right triangle. And I'm trusting you could get that. So I've completed the triangle. And now I just have to go and look at what I was interested in. I was interested in cosecant, right? Which is the reciprocal of sine. So instead, sine is opposite over hypotenuse. So I want the reciprocal, so I want hypotenuse over opposite, right? So this is going to become negative 1/9 root x squared plus 9 over x plus c. There we go. Let's check this one. I feel like checking it. I don't know why. I usually don't like to check these, but let's check it. Because it seems odd to me, at least, that the derivative of that is this. But let's see if we can't make it work. If it doesn't work, then we messed up somewhere. But I feel pretty good about it. So how would we do this? Take derivative of this. Negative 1/9 is going to be sitting here, right? It's a constant. And then I've got quotient rule, don't I? Derivative of the top is 1 over 2 root x squared plus 9 times derivative of what's inside, 2x times the bottom, x, right? Minus derivative of the bottom, 1 times the top, all over bottom squared. All right. Don't need that anymore. I'm just checking my work, right? That's all I'm doing. This is equal to negative 1/9. Okay. These twos cancel. I have x squared over root x squared plus 9 minus root x squared plus 9, all of this over x squared, right? Okay, now I'm going to do something kind of cool here. If you look at this as being a fraction over 1, then I can flip this up like this, or you can bring it back here and then multiply it through. Right? That's legit move. So if I do that, flip that and bring it up, it's basically going to multiply this times 1 over x squared and this times 1 over x squared. That fair? Okay, I'm going to erase this. Okay. I know that right now we're all tempted to cancel that. Yeah, let's cancel it. Shit. Okay, let's do it. 1. Okay, here's where we are. Negative 1/9. And then we have 1 over root x squared plus 9 minus root x squared plus 9 over x squared. All right, I think that's where we are. And I want to put those together because I'm trying to get it back to a single term. So I'm going to get a common denominator. So to do that, I have to multiply this by x squared, x squared. That's why I didn't want to cancel it, because I knew I was going to need to put it back together. But, and then this, I need to do root x squared plus 9 on top, root x squared plus 9 on the bottom, right? And I'm starting to feel pretty good because look at my denominator. My common denominator is what? X squared root x squared plus 9? Yeah. So I just hope that that numerator turns out to be 1. We'll see. Well, actually, we have a negative 1/9 out here still. So negative 1/9. So I hope it turns out to be a negative 9 on top. Okay, so let's see. If I get x squared on there, right? And then when you put these two together, right, root times root, they go away. So aren't you left with x squared plus 9? But then there's a minus. So it's minus x squared minus 9. Yeah, it's exactly what I needed because the x squared is going to cancel and be left with a negative 9 up top. I don't know. I find that pretty freaking beautiful right there. Look, that's gone. And then we have negative 9 here, and multiply it by negative 1/9, right? That cancels with that. And what you're left with is 1 over x squared times root x squared plus 9. Wow, right? So I mean, the thing is, it works, right? I mean, that was a long process to get to it, I guess. The trigonometric substitution worked. And I think you would agree with me that the antiderivative did not look like it would yield that when we took its derivative, right? That's why it's so hard to go backwards, because you can't just look at it and be like, oh, sure, yeah, that's, sure, you just take derivative and that's that. You have to convince yourself sometimes, and the algebra here can be a little bit messy. All right, let's do another one. There's no such thing as too much fun. Let's skip B. B looks kind of boring. How are y'all feeling about this? It's a lot, it's long, right? It's hard, is that what you said? Oh, okay. It just seems like we just keep on adding like layers onto these things, right? You just keep on just adding more complexity. Like lasagna, yeah. Okay, look at this one. Okay, x cubed. Yeah, think lasagna, it's good stuff. 4x squared plus 9 to the 3/2 dx. All right, buckle up. This problem is pretty juicy here. It's like homeland lasagna, like from Sicily, deep Sicily. I know, I'm getting kind of hungry too. All right, first of all, the square root is not obvious. I mean, it is, but it's not like just the square root, right? So we first have to realize that this integral is x cubed over the square root of 4x squared plus 9, but then that quantity what? Cubed dx. All right. Now, we should also try and convince ourselves that this can't be done another way. And you might play with something for a little while here. A basic U substitution? Maybe. But I think you'd still run into problems. So I'm not going to go that way. I'm going to go trig sub, all right? But that does not look like any of the forms that we've had, right? The form that we have to have is a root, and then it's got to be a squared minus x squared, right? And what's the coefficient on x squared in the formulas? 1, right? It's like a squared minus 1x squared. Or it's got to be a squared plus 1x squared, or 1x squared minus a squared. We've never seen a 4 there, right? Yes? Can I do what? I can, but I would have to factor a 4 out, right? So if I factor a 4 out, I'd have to factor from here and here, right? Which is exactly what I'm going to do, all right? I need the coefficient of 1 first. Yeah, that doesn't seem right, but I'm going to factor a 4 out of 9. I remember, like in college algebra, I always tell my students, like, if you want to see the difference between like Cal 1 algebra, like this is college algebra, and then this is Cal 1 algebra. That is a difference of squares. It's root x plus root 2 times root x minus root 2. So like that college algebra level, this calculus 1 level, right? This is a difference of squares. It is? Yes, look, right? It is a difference of squares. You FOIL that out, you're going to get that. So me pulling a 4 out of here, even though this is not like an 8, it can still be done, right? It's just algebra, it's just a little bit cranked up. So let's do that part. So the first thing I'm doing is I'm going to try and get a coefficient of 1 on x squared. Okay, so I do it. I'm going to take this a little slow here because we have to be extremely careful with that cubed right there. Parenthesis cubed. So I'm going to pull a 4 out of the root. So or not of the root, out of the 2 terms. So there, 4 comes out of the x squared, right? So 4 came out here, and then what do I have to put here? 9/4, 9 over 4. And that, if you don't believe it, you should have seen this at some point in your life. So just multiply it back through, and you'll see that gives you back 9. So that's a very clever pulling out of a 4. And now, can I pull the 4 out of the root? It'll come out of the root as a what? A 2, right? But then I've got a cubed, right? So 2 cubed will turn it into an 8, and that can come out of the integral on the denominator. Do y'all see that? 4 comes out as a 2, 2 gets cubed as an 8, 8 comes out of the integral.
He's not coming out easy.
Yep, that's right. We're gonna have to force it. All right, here it comes. Somehow this integral threw up an 8 out on the outside. So 1/8 integral x cubed over. Now, down here we have root x squared plus 9/4, right? All of that cubed dx. Did I put dx over there? Oh, I forgot my dx right here. All right. Now it looks like one of the formulas, right? X squared plus a squared. So we have a root x squared plus 9/4, which means that our a here is finally something not boring. A is actually what? 3/2, 3 over 2. Because remember, that's a squared, right? So a would have to be 3/2. Now, what is the trigonometric substitution that we make when we see this? Tangent. X is equal to a tangent theta, right? So 3/2 tangent theta. Don't forget the a. Okay, sometimes students will forget that the a goes there. So x must be a tan theta. Then that root stuff, all the root stuff, x squared plus a squared, all that automatically turns into what? 3/2 secant. It's just secant theta? Is it secant squared? No, just secant. The dx is the part that's going to turn into the secant squared. So the root part just turns into 3/2 secant theta. The dx is the 3/2 secant squared theta d theta. All right. Shall we continue? All right. How are we doing on time? Good. Here we go. Forgot what I'm doing. 1/8 integral. Okay, so 1/8 integral. All right, here we go. X cubed. Well, that's x, right? And I got to cube that. Yes? I'm actually not going to cube it. I'm just going to write 3/2 cubed. All right? And the reason I'm going to do that is because I'm going to have some other things in other places that are going to cancel out. So just, because it's not, I mean, you could write 27/8, you could, but I'm just going to leave it like that. That's this cube now. Tangent cubed? Over. Okay, the root thing. This root thing right here turns into 3/2 secant theta, right? But then it's being cubed. So it's being cubed because of that, right? So I'm going to cube that and this. So hey, I have another 3/2 cubed, don't I? And then I have a secant cubed. Am I done? Nope. Don't forget dx. Dx must be replaced. And dx gets replaced with this. And that gets, I'm going to just tack it onto the outside, like 3/2 secant squared theta d theta. All right. That can go. I can cancel out the secant squared, right? Two of those factors cancel out with two of those, which leaves me with one of those, right? And the 3/2 can go outside? Okay, 3/16 is where we are. Integral. All right, so what's left? Tangent cubed on the top. What's on the bottom? Secant theta. And then d theta. Another integral with tangent and secant, but they're not both on top next to each other like last class. So switch it all to sine and cosine. 3/16 integral sine cubed theta over cosine cubed theta, that's tangent cubed theta, over secant, which is 1 over cosine theta. D theta. So I got fraction over fraction. Flip the cosine up, and that will cancel one of those cosines out, won't it? Shoot. This doesn't look good. I was really hoping for like a u du here. Like just a basic substitution? Maybe it is. Hold on. Let me see. This is 3/16 integral. We've got a sine cubed theta over a what? Cosine squared theta. D theta. Could I let sine hear me? Okay, well, you could let u be anything you want it to be, but will it work, right? So will it? If you let u be sine, cosine is the derivative. See, it's down there though. You don't want your derivative being downstairs, right? You want it upstairs. So we have sine to an odd, right? Maybe if we peel the sine off, that'll be sine squared. We can rewrite it as 1 minus cosine squared. And then let our u be cosine. And the derivative of it will be out here. Maybe? Let's try it.